In this particular video, I want us to talk about fundamental particles, that is particle physics. Fundamental particles in this case are the particles which we are going to talk as leptons. Leptons are examples of fundamental particles, and these are particles which cannot be broken into any smaller particles, and these are particles which don't have an internal structure. So example fundamental particles are actually electrons. We can talk of positrons. We can talk of neutrinos. We can talk of antineutrinos. Yeah, so these are fundamental particles. There's a group of other fundamental particles which are known as quarks. And the quarks are building blocks for hadrons. So we're going to say the fundamental particles which comprises of quarks. We are going to have a quark here, a quark, and then the charge on it, and then we are going to have antiquarks. Quarks are fundamental particles which are of 6 types, and that is usually denoted as of 6 flavors. We have the up quark, down quark, we have charm, we have strange quark, we have top, and we have bottom quark. So these particles that I've highlighted here, the symbol for an up quark is U, the symbol for a down quark is D, the symbol for a charm is C, the symbol for a strange is S, the symbol for a top is T, and the symbol for a bottom is B. Then they have charges. Each of the charge for this one is 2 over 3, 1 over 3, 2 over 3, 1 over 3, 2 over 3, 1 over 3. Then once you have enlisted that way, you are going to put positive, negative, positive, negative, positive, negative. So meaning an up quark has a charge of positive 2 over 3e. So these particles, which are quarks, are the ones that are going to be building blocks from non-fundamental particles. Like for instance, we can talk of a proton, and we can talk of a neutron. A neutron is a proton is made up of a proton is made up of 2 up quarks plus a down quark, and a neutron is made up of 1 up quark and 2 down quarks. So that is why we are saying that quarks are actual building blocks for other particles which we call hadrons. So every quark has got an antiquark. For instance, the up has an antiquark which is U, as a down quark has a antiquark D bar, C bar, S bar, and then we have T bar, and we have the bottom bar. But the charge now, they have the same mass, but they have the opposite charges. So this is going to have a charge of what? This is going to have a charge of 2 over 3, and this is going to be positive 1 over 3, minus 2 over 3, positive 1 over 3, minus 1 over 3, 2 over 3 rather, and positive 1 over 3. So if you want to basically generate for instance a neutron, you need to have an up quark which is having a charge of what? 2 over 3, plus a down quark. A down quark is 1 over 3 negative plus negative 1 over 3. So you can see the charge of a neutron is usually what? Is usually 0, isn't it? So that is how they combine. Then I'm going to take you through the exam questions whereby this concept has been tested, so that you can be able to see how you answer the questions. So we are going also to talk about hadrons. Hadrons are made up of quarks. Hadrons are particles which are made of quark, and we have types of hadrons. In this case, we have the first type is a meson, and we have a baryon. A meson is made up of a quark and antiquark. Yeah, and a baryon is made of 3 quarks. Okay, so the difference between a meson and a baryon is that baryons are made of combining 3 quarks, but mesons are made by combining a quark and antiquark. Now, for instance, you can have an up quark, then you combine it with antiquark of a strange. Yeah, you see, you are going to have a particle. But particles such as protons and neutrons, these are type of hadrons which are known as what? Baryons. Okay. So at this point, I want to take you through different questions which which have been asked in various exams, so that you can be able to know how do you answer questions to do with fundamental particles. Actually, that is particle physics. So for instance, you can be given a question whereby you are supposed to state which family it belongs. So let's just dive in so that we can be able to see how do you really answer questions when it comes to AS Physics of Cambridge exams. And if you are new to Proflan YouTube channel, consider subscribing so that anytime I'm going to upload a tutorial, you'll be notified. See you. Let's dive in. Let's go in so that we can be able to look into this particular part. So what I'm going to do here, is that I'm going to scan this document so that I can be able to upload it so that you can be able to see how it works. Let me just scan this document. The family, the group that contains neutrino, electrons, and the positrons, those are called leptons. Now, a hadron P has a charge of 1e, where E is the elementary charge, and the hadron P is composed of a down antiquark. So something that you need to remember, antiquark, basically a down antiquark has got a charge of positive 1 over 3. That is a down antiquark. Then since it's made of another quark, then it will be 1 over 3 plus x should give us the charge that we are being told here, 1. So meaning that this is going to be what? Implying that our x is going to be 1 minus 1 over 3, which means this is going to be negative what? Rather positive 2 over 3. So a particle that has positive 2 over 3, that particle is known as what? Dr. P. Okay, so if you can be able to check, you will realize that a particle that has positive 2, it could be positive 2 over 3, it could be an up quark, it could be a charm, or it could be a top. So that is why you see I've just selected this, because they are going to, those are the particles which have the charge that was mentioned at that point. Now state the type of hadron in P. The hadron of P is comprises of two particles. That's a quark and antiquark, and that is actually a meson because it's made up of a quark and antiquark. So the next part here, you are told that Q undergoes radioactive decay to form R. So Q decays to form R, and an antineutrino is formed. Antineutrino is formed when we have beta minus decay. That's when an antineutrino is formed. Then it means that this particle X that we have here is actually an electron which has this charge. That's why you can see I've indicated -1 here, and I've indicated 0 as the mass of an electron. Then now, if for instance this was having P and was having maybe let's say an N down here, and this is P up here and an N down here, then you can see that this should be N+1 because of this negative that we have here, so that we can have it balanced, the equation balanced on the other side. So we are supposed to state the particle X. The particle X is actually an electron, and compare the nucleon of particle P, Q and R. The nucleons of Q and R, the nucleons are the numbers we have at the top here. They should be the same because this mass of an electron is actually 0, and the mass of a neutrino is 0, antineutrino is 0, and the charge of antineutrino is also 0. Then the nucleon of Q and R are the same. Then if we are talking about the charge of R, the charge of R is going to be greater than the charge of Q, because you can see R has one extra proton, has one extra proton. So these are just the flavors, the 6 flavors of quarks: up, down, charm, strange, top and bottom, in that order, with the corresponding charges and antiquarks for that case. So that is one way the question can be asked. And then we have the second part here, whereby we are told that state the name of the group of particles that includes Q and R. But what is Q and R? We are told that particle Q and R are composed of one quark and antiquarks. Those are actually called hadrons, but to be very specific, those are mesons. Yeah, this is general, because hadrons is a general term for particles which are made of quarks. So mesons are usually made of one quark and one antiquark. Another group of hadrons is what we call the baryons, and the baryons are actually made up of what? 3 quarks. All right, so let's look at the next part. Q has a charge of -E, where E is the elementary charge of R. It has a charge 0. So we are told that Q has the first particle, which is a strange. And what's the charge for a strange? Let's look at strange. A charge for a strange is actually -1/3. Yeah, the charge for a strange is -1/3. So I can be bigger, and then we can say -1. Let me just write here, -1 is equals to the charge of a strange, because this is the overall charge. So that's why I'm saying -1 is equals to charge of a strange is 1/3 negative, plus the one that we don't understand for the second quark here. So if I take this on the other side, I'm going to have -1 plus 1/3 is equals to our x, and in that case our x is going to be -2/3. So the second quark is going to be any particle or any quark that has got a charge of -2/3. So if you look at this, -2/3 is going to be ant up, could be ant charm, could be ant bottom, ant top rather, ant top. So could be any of those particles. in that particular case. So that's why you can see is could be anti-charm, anti-bottom, anti-top on that. So there is another R which has a charge 0. In order to find this one, we are going to say 0 is equals to what? Or -2, because this is an anti-up. An anti-up has -2/3. So -2/3 plus x, because is this type of particle is made of anti-up and another particle which we don't understand. So we are going to say -2/3 because that is the charge for the anti-up, plus x, which we don't know, is equals to 0. So basically that is going to be 2/3. So which particle has a charge of 2/3? You need to understand is either an up, a quark, or a charm. Yeah, so which you can be able to see alongside here. I've just written here. It could be, of course, this is positive, negative, positive, negative, positive, negative. So it could be an up quark, it could be a charm, it could be a top. So any of them could be able to fit in this given point. So basically that's how you answer such questions. And here you are told the nucleus of isotope samarium as contains 62 protons and 85 neutrons. So nucleon number is actually the sum of this and this, which is going to be 147, and proton number is going to be 62 in that case. Now, isotope of samarium is radioactive and decayed by emitting particles. Gamma radiation is not emitted. So the energy spectrum of emitted particles are shown, which is actually discrete because we have only one value here. So we are supposed to explain how this figure shows that this isotope samarium emit alpha particles and does not emit beta particles. If we were talking about beta particles, we are going to have a continuous range of energies if it's actually beta particles. But since we have a discrete and only one value of kinetic energy, then this means this is a alpha particles being emitted. So that's how you are supposed to answer that question. Then isotope of samarium decays to an isotope neodymium. So meaning samarium is decaying to neodymium, giving what? Giving an alpha particle. So remember, alpha has got 4 and 2 like that. Then since we had written this is 147 and this is 62, then we can be able to balance here. So this is going to be 143 and this is going to be 60. So you can see now the charge for samarium and neodymium are different. The charge for this one is higher, the charge of this one is less by 2 values. So we have baryon is composed of 3 quarks. So baryon is composed of 3 quarks which all have different flavors. We said baryon is a type of hadron that is made of 3 quarks, but we have meson. Meson is a type of hadron that is made up of 2 quarks, and that is a quark and anti-quark, right? So we are supposed to determine in terms of elementary charge, because we are told 2 of the quark is an up quark and we have a bottom quark, and we are told the charge for this type of baryon that has been formed is actually an up. So an up is 2/3. A bottom is -1/3, plus an x must give us the charge of that particular baryon that has been formed. We have been told the charge is 0, isn't it? So we have to equate that, and if you try to work it out, it's going to be -1/3. So the charge will be -1/3. And if we are supposed to state the flavor of that third quark, in that case the flavor could be what? Let me just take you back to the list that I'd enlisted here. It's -1/3, so it could be a Dunn quark, It could be a strange quark, or it could be a bottom quark. So that is exactly what we are going to do in that particular question. Please, if you are new to ProfLearn YouTube channel, consider subscribing so that anytime I'm going to upload another video, you'll be notified. So it could be any of this. It could be a strange, it could be a down, or it could be a bottom in that particular case. So let us see what further could be asked. Nuclei X are different isotopes of the same elements. Nuclei X are different isotopes of the same elements. Are different isotopes of the same elements, X and Y. So meaning they have the same proton number. Nuclear X is unstable and it emits beta plus particles. So then we are supposed to compare the number of protons in each nucleus and state and explain whether the charge nucleus X is less than or greater than that of Y. So they have the same number of protons because if we are talking of X and Y, since they are isotopes, they have the same number of protons. So they have the same number of protons. Nuclear Z, X has one more protons than Z, has one more proton than Z, because if it's decaying to become Z, X decays. Let's look at X decays to form Z, and Z is emitting beta plus. That is a positron. Yeah, one. So this is going to be, if for instance this is P and this is Q, this is 0. This is going to be P because the mass number here is 0, and Q, this is a positive, so this is going to be Q minus 1. But remember, for beta plus decay, we are going to have a neutrino being emitted, and the neutrino has mass and 0 and the charge being 0. So if you see the Z that we are forming here as one proton less, so that's why we have it as one more. X has one more proton than Z, or Z has less proton by one proton less. So X has a greater charge than Z because X has more proton than Z. So that's why we are going to look at that. Hadrons can be divided into two classes, P and Q. Group Q is baryons. Baryons, we can say baryons or baryons. Then state the name of Q. Q is mesons. Describe in general terms quark structure of hadrons belong to group Q. Q is mesons, isn't it? And they are made up of two quarks, and that is a quark and antiquark. They are made of quarks and antiquark. So I believe you are getting value on how to approach this question, and this question actually is like the question that we have done in the previous section. So maybe an isolated stationary nucleus X decays by emitting alpha particles from nucleus to form nucleus Y. So X decays to form Y by emitting alpha particles. Now nucleus Y and Z are isotopes. Y and Z are isotopes. So we have this Y that we have generated here, and the Z are isotopes. So meaning they're going to have the same proton number. Because if this has a proton number of n-2, which is obtained from here, then also it means that Z is going to have the same proton number. That's why I highlighted that here so that you can be able to see. What is going to be different is going to be the nucleon number. The nucleon number for Y and Z will be different, but the proton number will be the same because they are isotopes. All right, let's proceed. Yeah, by comparing the number of protons in each nucleus, state and explain whether the charge in Y is less than or greater than or the same as the charge in Z. Charge in Y, they have the same charge because they have the same number of protons, because they have the same number of what? The number of protons. But when we are talking about the nucleus of X, the nucleus has a greater charge than Y. Why is that? You can see here this has n, but this has n minus 1. So we're going to say X has a greater nuclear charge. Now, use the principle of conservation of momentum to explain why nucleus of Y cannot be stationary immediately after the decay of the nuclear X. So, when this decays, when this X decays, it leads to the formation of Y. But for the formation of Y to take place, an alpha particle is going to be ejected. An alpha particle is going to be ejected. So remember the law of conservation of momentum state what? The law of conservation of momentum. Momentum before collision is equal to momentum after collision. So this means the total momentum has to be conserved. So the total momentum after collision. So the nucleus Y should have equal and opposite momentum to the alpha particle which is being ejected. So since an alpha particle is being ejected and it will be having a momentum, then this particle Y should also have a momentum in the opposite direction. So if this particle is going to have a momentum in the opposite direction compared to the alpha particle that has been ejected, that will mean that the nucleus Y is not going to be stationary because it will be having a momentum in opposite what? Direction. So it must be having a velocity. So that's why I'm saying that according to the law of conservation of momentum, momentum before collision should be equal to momentum after collision. So Y nucleus should have equal opposite momentum to that of an alpha particle, so it must have a velocity. It must have a velocity in the opposite direction, so cannot be stationary. So basically that's what we were to highlight in that particular question, and the rest of the questions here are just to guide you on how to answer questions, so you can be able to look at the question that was asked. Yenda ngosari ora kusiri sakali yagenda kuchoro. Yenda ocheki sari kusiri sakali nendo iromo na kuchoro. Harakisha. Minyoka. So the rest of the question that I've highlighted here, you can be able to go through them on how to answer those questions, and I would like you to join the Patreon class so that you can be able to join my Patreon group so that you can be able to download this PDF that I was working on this particular question. So that is what we are going to talk about in this area, and it means that with those questions that have been mentioned in that worksheet, in fact you can be able now to approach different and various questions related to particle physics. And if you really got value from this particular video, give this particular video a thumbs up, and also you consider subscribing. Share this video to your friends, encourage them also to subscribe. I really wish you the best, and if there's any videos you would like me to prepare on, especially for A-level physics and A-level math, you can be able to leave a comment down below so that I can be able to prepare it. If you learned something new in this particular video, just leave a comment down below. Don't forget to share this video and don't forget to subscribe. See you in the next video.